Gravity enters physics as a rule that works before it enters as something that is understood. Long before questions about space-time curvature information or entropy arise, gravity is encountered as a reliable pattern in motion. Objects fall, planets orbit, and trajectories repeat with mathematical regularity. The earliest successful theory of gravity does not attempt to describe the nature of this phenomenon. It restricts itself to prediction. It tells us how bodies move and nothing more. In the classical formulation developed by Isaac Newton, gravity is defined through a precise quantitative relationship. Every object with mass attracts every other object with a strength that depends on their masses and the distance separating them. This rule allows the calculation of acceleration at every point in space, provided the positions of masses are known. With this single law, the motion of the moon, the fall of an apple, and the paths of planets around the sun can be predicted with extraordinary accuracy. The power of the theory lies in its universality. The same mathematical structure governs motion on Earth and motion in the heavens. There is no distinction between terrestrial and celestial physics. This unification was unprecedented. It established gravity as a central interaction governing the large-scale structure of the universe. Yet this success hides a limitation that is easy to overlook. The law specifies how gravity acts, but not what gravity is. Newtonian gravity is formulated entirely in terms of forces and motion. Given a force, the theory tells us how an object accelerates. It does not explain where the force comes from or how it is transmitted. Gravity appears as an interaction that acts directly across space, without delay or medium. Two objects influence one another instantaneously, regardless of distance. This feature, later described as action at a distance, was deeply unsettling even to Newton himself. The discomfort arises because the theory offers no mechanism. There is no carrier, no signal, and no physical process connecting separated masses. The force simply exists as a mathematical relation imposed on matter. Gravity in this framework is not something that unfolds in time. It is not something that propagates. It is simply there everywhere at once. To make this formulation possible, Newtonian gravity relies on a fixed background structure. Space is assumed to exist as an absolute three-dimensional arena extending uniformly in all directions. Time is assumed to flow at the same rate everywhere, independent of motion or position. These entities are not influenced by matter or energy. They exist prior to physics and remain unchanged by it. Within this background, gravity acts as an external rule. Objects move through space and time under the influence of forces, but space and time themselves never respond. This separation is essential to the theory. Without absolute space, the notion of distance loses meaning. Without absolute time, acceleration cannot be defined. Gravity therefore depends on structures it does not explain. Despite this conceptual fragility, the empirical success of the theory is overwhelming. Predictions based on Newtonian gravity match observation across the solar system with remarkable precision. Planetary orbits, eclipses, tides, and the return of comets all follow from the same equations. For centuries, no competing theory could match its accuracy. This success delayed deeper questions. Yet success does not equal completeness. Newtonian gravity achieves prediction by assumption. It assumes the equality of inertial mass and gravitational mass without explanation. It assumes universality rather than deriving it. It assumes instantaneous influence without providing a physical reason. These assumptions are not errors. They are limitations built into the framework. Most importantly, the theory does not address ontology. It does not tell us what gravity is made of or whether it has internal structure. It does not tell us whether gravity has degrees of freedom of its own. It does not tell us why gravity couples to all matter equally. These questions lie outside its scope. Newtonian gravity therefore occupies a precise position in physics. It is a kinematic theory, not a dynamical one in the deeper sense. It specifies motion given forces, but does not specify the origin of those forces. It treats gravity as fundamental by declaration rather than by derivation. It works because nature obeys it within its domain, not because it reveals the underlying structure of reality. This distinction becomes critical once physics begins to demand explanation rather than prediction. As other interactions are reformulated in terms of local fields and finite propagation speeds, gravity remains an outlier. It resists reduction to microscopic constituents. It does not fit naturally into a framework where interactions arise from exchange processes or internal degrees of freedom. At this stage, gravity is known operationally, but not conceptually. It governs motion with precision while remaining physically opaque. The theory answers the question of how objects move under gravity while leaving unanswered the deeper question of what gravity actually is. That unanswered question is not a philosophical luxury. It is the pressure point that will eventually force a transformation in how gravity is understood. The limitations of Newtonian gravity become clearer as physics advances beyond simple motion. The theory assumes that space and time provide a fixed stage on which events unfold. Distances are measured against an unchanging geometric backdrop. Durations are measured by clocks assumed to tick uniformly everywhere. Gravity influences objects, but never influences the standards by which motion is measured. This separation between dynamics and geometry is built into the foundations of the theory. As long as measurements are coarse, this separation remains invisible. Falling bodies accelerate, as predicted. Orbits repeat. But once precision increases, the assumptions begin to matter. If gravity acts on all matter without exception, then the instruments used to define distance and time must also be subject to its influence. A theory that treats rulers and clocks as immune to gravity while allowing gravity to act universally is internally strained. The problem deepens when gravity is compared to other interactions. Electromagnetism, for example, is described through fields that exist at every point in space and evolve in time according to local equations. Changes propagate at a finite speed. Cause and effect are connected through continuous processes. Newtonian gravity lacks this structure. It does not assign gravitational influence to local degrees of freedom. There is no gravitational field with independent dynamics in the original formulation. There is only a force law applied instantaneously. This absence of locality is not a technical detail. It undermines the coherence of the theory once relativity enters physics. Instantaneous influence across arbitrary distances conflicts with the idea that information cannot propagate faster than light. While Newtonian gravity predates this constraint, its structure becomes incompatible with later principles. The theory works numerically, but resists integration with a broader physical framework. Another limitation appears in the treatment of energy. In Newtonian gravity, gravitational potential energy is defined relative to an arbitrary reference point. It is not localized. There is no meaningful way to assign gravitational energy to a region of space. This contrasts sharply with other interactions where energy density can be defined locally. The absence of gravitational energy density hints that gravity may not fit the same conceptual mold as other forces. The equality of inertial mass and gravitational mass provides another clue. In Newtonian mechanics, inertial mass determines how an object responds to force, while gravitational mass determines how strongly it participates in gravitational interaction. Experimentally, these two quantities are identical to extremely high precision. Newtonian theory has no explanation for this fact. It must be imposed by hand. The coincidence is exact yet unexplained. This exactness is not trivial. If gravity were merely another force, there would be no reason for all objects to accelerate identically, regardless of composition. Electric forces do not behave this way. Nuclear forces do not behave this way. Gravity does. This universality suggests that gravity is tied not to a property of matter, but to something more general. Newtonian gravity cannot accommodate this insight because it treats gravity as an external interaction. rather than a structural feature. As observational astronomy improves, further discrepancies appear. The orbit of Mercury deviates slightly from Newtonian prediction. The deviation is small but persistent. Attempts to explain it within the Newtonian framework require ad hoc modifications. These adjustments preserve prediction but erode conceptual clarity. The theory begins to show signs of strain at its boundaries. None of these issues immediately falsify Newtonian gravity. Within its domain, it remains extraordinarily successful, but they reveal a pattern. The theory is predictive, but not explanatory. It relies on fixed background structures it cannot justify. It assumes universality it cannot derive. It treats gravity as fundamental while leaving its nature undefined. At this point, gravity occupies an unusual position. It is the most familiar interaction and the least grounded conceptually. Its equations work, but its interpretation is unstable. It explains trajectories, but not causes. It assumes space and time, rather than explaining them. These features are not flaws to be patched. They are signals that the framework has reached its natural limit. The need for a deeper description does not arise from dissatisfaction with numbers. It arises from the demand for coherence. Physics seeks not only to predict, but to understand. A theory that cannot explain its own assumptions invites replacement. Newtonian gravity does not fail, it becomes insufficient. This insufficiency sets the direction forward. The path does not involve adding complexity to the force law. It involves questioning the background on which the law is written. If gravity acts universally, then space and time themselves cannot remain untouched. If all objects fall the same way, then free fall must be understood differently. The final pressure comes from universality itself. Gravity does not discriminate. Every form of matter and energy responds in exactly the same way. Composition, shape, and internal structure do not matter. This fact is not approximate. It is exact to the limits of measurement. Such universality is unlike any other interaction in physics. It demands explanation. If gravity were a conventional force, then different objects would respond differently depending on their internal properties. This is what occurs with all other known interactions. Gravity alone ignores those distinctions. The only quantity that matters is energy. This behavior cannot be accidental. It implies that gravity is not acting on matter in the usual way. It is acting on something more fundamental. Once this is recognized, the fixed background of Newtonian physics becomes untenable. If gravity affects all matter, then it must also affect the physical systems used to define measurement. Clocks are physical objects. Rulers are physical objects. If gravity acts on them, then measurements of time and distance cannot be independent of gravitational environment. The separation between force and geometry collapses. Newtonian gravity cannot incorporate this insight. Its structure forbids it. Space and time are assumed to be absolute from the outset. They cannot bend, stretch, slow, or respond. Gravity acts within them but never on them. Universality therefore remains unexplained because the framework has no place to put it. This marks the true end of gravity as a classical interaction. The problem is not mathematical inconsistency. The problem is conceptual exhaustion. Every attempt to push the theory deeper runs into assumptions it cannot justify. The equality of inertial and gravitational mass remains unexplained. The absence of gravitational propagation remains unresolved. The immunity of space and time remains artificial. The resolution will not come from refining the force law. It will come from abandoning the idea that gravity is a force at all. The universality of free fall points to a different interpretation. Objects under gravity are not being pushed or pulled. They are following natural paths defined by the structure of space-time itself. This idea does not modify Newtonian gravity. It replaces its foundation. Space and time cease to be passive backgrounds. They become physical entities capable of change. Gravity ceases to be something that happens within space-time. It becomes something that space-time does. This transition preserves everything Newtonian gravity gets right while explaining what it cannot. It explains universality without assumption. It eliminates action at a distance. It gives gravity a mechanism without introducing new forces. Motion under gravity becomes inertial motion in a curved geometric environment. The classical force picture therefore ends not in failure, but in transformation. Newton provided the correct rules for motion within a limited framework. What follows will reveal why those rules work. Gravity will no longer be defined by force laws acting on matter. It will be defined by the geometry of space-time itself. The transition from force to geometry begins with a single experimental fact that cannot be ignored. All objects fall in the same way. A stone, a piece of wood, and a block of metal released together accelerate identically in a gravitational field when air resistance is removed. This behavior does not depend on mass composition or internal structure. It is exact to the limits of measurement. This fact was known long before it was understood, but its significance only becomes clear once gravity is examined carefully. In Newtonian physics, this universality is imposed rather than explained. Inertial mass and gravitational mass are declared equal because experiment demands it. There is no deeper reason. In a geometric interpretation, this equality is no longer mysterious. It becomes inevitable. If gravity is not a force acting on objects but a feature of space-time itself, then all objects must respond identically. Motion under gravity is no longer forced motion. It is natural motion. This insight is captured by the equivalence principle. Locally, there is no experiment that can distinguish free fall in a gravitational field from motion at constant velocity in empty space. An observer inside a freely falling elevator experiences weightlessness. Objects float, clocks tick normally. Physical laws reduce to those of non-accelerated motion. Gravity disappears locally. This is not an approximation. It is a statement about the structure of physical law. If gravity can be eliminated locally by choosing the appropriate frame of reference, then it cannot be a conventional force. Forces do not vanish by changing perspective. Geometry does. The straightness of a path depends on the geometry in which it is defined. From this point, the interpretation of gravity changes fundamentally. Objects under gravity are not being pulled. They are following the straightest possible paths available to them. These paths appear curved only because space-time itself is curved. What is perceived as gravitational acceleration is actually inertial motion in a non-Euclidean geometry. To make this precise space and time must be unified. Motion is not described by trajectories through space evolving in time, but by paths through space-time as a single four-dimensional entity. Distance and duration are no longer separate concepts. They combine into space-time intervals that depend on motion and gravitational environment. In this framework, space-time is no longer passive. It becomes dynamical. The presence of mass and energy alters its geometry. Paths that were once straight become curved. Clocks tick at different rates depending on gravitational potential. Rulers measure different distances depending on position and motion. Geometry responds to physics. Gravity therefore ceases to be something added to space-time. It becomes space-time. There is no gravitational field acting within a fixed background. The background itself is the field. Curvature replaces force as the explanation for motion. This shift resolves every conceptual problem faced by Newtonian gravity. Universality is explained because geometry defines motion for everything. Action at a distance disappears because changes propagate locally through space-time. The equality of inertial and gravitational mass becomes a consequence rather than an assumption. Space and time are no longer immune to gravity. They are its substance. The mathematical framework that captures this idea is general relativity. In this theory, the geometry of space-time is governed by equations that relate curvature to energy and momentum. These equations do not describe forces acting on matter. They describe how space-time responds to the presence of matter and how matter responds to that geometry. The power of this description lies in its economy. no new forces are introduced. No additional assumptions are required beyond the equivalence principle and the demand for consistency. Gravity becomes inseparable from measurement itself. Motion, time, and distance are all shaped by geometry. At the same time, the theory remains classical. Space-time is treated as a smooth, continuous entity. Curvature varies continuously from point to point. There is no discreteness, no quantization, and no microscopic structure assigned to space-time. Geometry replaces force, but does not yet reveal what geometry is made of. This distinction will become critical later. For now, the achievement is clear. Gravity has been reinterpreted without loss of predictive power and with enormous gain in conceptual coherence. The force picture has been abandoned. In its place stands a geometric description that explains why gravity behaves universally and why it resists treatment as a conventional interaction. Yet geometry alone is not the final word. It explains how gravity works, but not whether space-time itself has deeper structure. The theory answers questions Newtonian gravity could not while opening new ones of its own. Gravity has become geometry. The next task is to understand what geometry ultimately represents. The geometric picture of gravity gains its full meaning through the structure of general relativity. In this framework, space-time is described by a metric that determines how distances and time intervals are measured. This metric is not fixed. It changes in response to energy and momentum. Matter and radiation do not move through space-time as if it were a rigid container. They shape it continuously. The relationship between geometry and energy is encoded in equations that equate space-time curvature with the distribution of energy, momentum, and stress. These equations are local. They do not refer to distant masses acting instantaneously. They describe how space-time bends at each point as a response to what is present there. Changes propagate through space-time at a finite speed. Gravity becomes causal. One immediate consequence is the behavior of light. In Newtonian physics, light is unaffected by gravity because it has no mass. In the geometric picture, light follows the same rules as everything else. It travels along the straightest possible paths defined by space-time geometry. When space-time is curved, those paths bend. Light does not feel a force, it responds to geometry. This prediction was confirmed when starlight passing near the Sun was observed to shift its apparent position. The effect was small, but decisive. Time itself becomes part of the dynamical structure. Clocks placed at different gravitational potentials tick at different rates. A clock deeper in a gravitational field runs more slowly than one farther away. This effect is not mechanical. It does not arise from interference or resistance. It arises because time itself is stretched by curvature. This phenomenon has been measured directly using precise clocks and must be accounted for in satellite-based navigation systems. General relativity also predicts the existence of gravitational waves. When massive objects accelerate, they disturb the geometry of space-time. These disturbances propagate outward as waves carrying energy and information. Space-time is not rigid. It is elastic. The detection of these waves confirmed that geometry is a physical entity capable of dynamical behavior. Despite these successes, the theory remains classical. Space-time is treated as a smooth continuum down to arbitrarily small scales. There are no atoms of space or time. Curvature varies continuously. The equations describe average behavior rather than microscopic structure. This classical character is both a strength and a limitation. It is a strength because it provides a precise and accurate description of gravity across a vast range of scales. From planetary motion to cosmology, the geometric picture works extraordinarily well. It unifies gravity with the structure of space-time itself. It explains why gravity is universal and why it cannot be screened or turned off. It is a limitation because it leaves unanswered questions. The theory does not explain what space-time is made of. It does not assign degrees of freedom to geometry. It does not describe how spacetime behaves at the smallest scales where quantum effects dominate everything else. Geometry is treated as fundamental but featureless. This absence becomes increasingly significant when gravity is compared to other areas of physics. Matter and radiation are described by quantum theory. Energy comes in discrete units. Fields fluctuate, yet the spacetime in which these processes occur remains perfectly smooth. The coexistence of quantum matter with classical geometry is conceptually unstable. It works in practice but resists unification. Another tension appears when time symmetry is considered. The equations of general relativity do not prefer a direction of time. They allow processes to run forward or backward equally. Yet the universe exhibits a strong arrow of time. Entropy increases, structures form, stars evolve. The geometric description alone does not explain this behavior. These observations do not undermine the geometric picture. They define its boundary. General relativity explains how gravity works at the classical level. It does not explain whether geometry itself has microstructure. It does not explain why spacetime carries entropy. It does not explain how gravity fits into a quantum description of nature. Geometry therefore replaces force as the explanation for gravitational motion. But geometry itself becomes a new object of inquiry. It behaves dynamically. It responds to energy. It carries waves. Yet it remains smooth and continuous. The question shifts from how gravity acts to what spacetime is. This shift marks a deeper transition. Gravity has become geometry. The next step will ask whether geometry is fundamental or whether it emerges from deeper statistical and informational principles. To answer that question, physics must move beyond classical descriptions and confront entropy directly. The final aspect of the geometric description concerns its scope and its silence. General relativity succeeds by elevating space-time from background to participant. It explains gravitational motion as a consequence of curvature rather than force. It removes action at a distance and replaces it with local causal dynamics. It explains the universality of free fall and the equality of inertial and gravitational mass without assumption. In every classical test, it performs with extraordinary accuracy, yet the theory also draws a clear boundary around itself. It is a theory of smooth geometry. It assigns no internal degrees of freedom to spacetime beyond curvature. There is no notion of spacetime entropy built into its foundations. There is no accounting of microscopic states. Geometry responds deterministically to energy and momentum, but does not fluctuate thermally. Spacetime curves, but it does not count. This absence becomes impossible to ignore when gravity is pushed into extreme regimes. In regions of very strong, curvature horizons form. Information becomes inaccessible. Observers lose contact with parts of spacetime. These are not optional features. They follow directly from the equations. Yet the theory itself provides no language to describe what is lost or how that loss should be quantified. Geometry predicts horizons, but remains silent about their informational meaning. Another limitation emerges from continuity. Because spacetime is assumed smooth at all scales, the theory permits arbitrarily small structures and arbitrarily high curvature. Nothing in the equations signals a breakdown. There is no natural cutoff. This stands in contrast to quantum physics, where discreteness and uncertainty appear inevitably. The smoothness of geometry is an assumption, not a conclusion. This assumption works as long as gravity remains classical. But once quantum effects are considered, the coexistence becomes strained. Quantum fields fluctuate. Energy densities become uncertain. If energy fluctuates, then curvature must fluctuate as well. A perfectly smooth spacetime cannot remain consistent with quantum matter. The geometric description resists integration with quantum principles not because of technical difficulty, but because of conceptual mismatch. Time symmetry deepens this tension. The equations of general relativity allow collapse and expansion equally. They do not encode an arrow of time, yet gravitational systems clearly participate in irreversible processes. Stars form, evolve, and burn out. Structure grows from uniformity. The geometric description captures motion, but not irreversibility. It explains trajectories, but not direction. These observations do not weaken the theory. They clarify its role. General relativity is a complete classical description of gravity. It is not a microscopic theory. It does not claim to describe the fundamental constituents of spacetime. It provides an effective macroscopic language that works extraordinarily well where quantum effects are negligible. The importance of this distinction cannot be overstated. Geometry in general relativity plays a role similar to pressure or temperature in thermodynamics. It describes collective behavior without revealing underlying structure. It is precise and predictive without being fundamental in the deepest sense. This realization does not imply that gravity must be emergent. It implies that the geometric description alone does not answer all questions. Spacetime behaves as if it has internal structure, yet that structure is invisible to classical equations. The theory works because it averages over whatever that structure may be. The geometric reformulation of gravity therefore represents both an endpoint and a beginning. It resolves the failures of the force picture while introducing new mysteries. Gravity is no longer a force, but curvature. Spacetime is no longer passive, but dynamical. Yet geometry itself becomes the next object of investigation. The question that now arises is not whether gravity is geometry. That is established. The question is whether geometry itself carries entropy and information. If it does, then spacetime cannot be fundamental in the same way classical descriptions assume. The next step will bring thermodynamics into direct contact with gravity and expose a connection that geometry alone cannot explain. Entropy enters physics not as a vague idea about disorder, but as a precise quantitative concept rooted in counting and probability. Its origin lies in the realization that physical systems contain an overwhelming number of microscopic constituents whose exact behavior cannot be tracked in detail. When systems become large, physics changes character. Exact trajectories give way to statistical descriptions. Entropy is the quantity that makes this transition precise. The central insight comes from the work of Ludwig Boltzmann. A physical system can be described at two fundamentally different levels. At the microscopic level, every particle has a position and a momentum. If all of these quantities were known exactly, the future and past evolution of the system would be determined by time-symmetric laws of motion. At the macroscopic level, only a small number of collective variables are specified, such as total energy volume and particle number. These variables define what is called a macrostate. A single macrostate corresponds not to one microscopic configuration, but to an enormous number of them. Each distinct microscopic arrangement consistent with the same macroscopic description is called a microstate. The key point is that the laws of physics do not distinguish between these microstates. They are all equally valid realizations of the same macroscopic condition. Entropy is defined as a measure of how many microstates correspond to a given macrostate. The larger the number of compatible microstates, the higher the entropy. This definition is exact and mathematical. It does not rely on subjective interpretation. It does not depend on visual appearance. It depends only on counting. This perspective immediately reframes thermodynamics. The second law does not state that systems must become more chaotic. It states that systems evolve toward macrostates that can be realized in more microscopic ways. Given two macrostates, one with few microstates and one with many, the system is overwhelmingly more likely to move toward the latter simply because there are more ways to be there. Irreversibility emerges from probability, not from dynamics. The microscopic equations governing particle motion are time-symmetric. They allow trajectories to be reversed exactly. Nothing in those equations prefers past over future. The arrow of time arises because low-entropy macrostates are extraordinarily special. They occupy a tiny region of the space of possibilities. High-entropy macrostates dominate that space. Once a system begins in a low entropy state, almost any evolution will increase entropy. Evolutions that decrease entropy are not forbidden. They are merely fantastically unlikely. For systems with a large number of particles, the probability of spontaneous entropy decrease becomes so small that it can be ignored for all practical purposes. Determinism at the macroscopic level emerges from statistics rather than certainty. This statistical origin of the arrow of time is crucial. Entropy increase is not driven by a force. It is not encoded in fundamental laws. It reflects missing information. When a system is described macroscopically, almost all microscopic detail is ignored. Entropy quantifies that ignorance. It measures how much information about the exact microstate is absent. This interpretation eliminates a common misconception. Entropy is not disorder. Many high-entropy states are highly uniform and structured. A gas evenly distributed in a container has higher entropy than the same gas confined to one corner, even though it appears more ordered. What matters is not appearance, but multiplicity. Uniform distributions can be realized in vastly more microscopic ways. Equilibrium is understood in the same way. A system at equilibrium is not static. Microscopic motion continues relentlessly. Equilibrium means that the system occupies a macrostate with maximal entropy given its constraints. Fluctuations occur, but they average out because the overwhelming majority of microstates correspond to the same macroscopic values. Crucially, entropy depends on what is counted as a microstate. This dependence anchors entropy to the physical degrees of freedom of the system. For a gas, the microstates are particle positions and momenta. For a magnetic system, they may involve spin configurations. Entropy is not an abstract label imposed from outside. It is rooted in the structure of the system itself. This grounding becomes decisive once gravity enters the discussion. In ordinary thermodynamic systems, the microscopic degrees of freedom are known. In gravitational systems, they are not. When entropy appears in gravitational contexts, it cannot be interpreted automatically. It becomes a signal that something deeper is at work. Before gravity can be brought into contact with entropy, the statistical meaning must be clear. Entropy measures missing information. It arises from counting microstates. It explains irreversibility without altering time-symmetric laws. It depends on underlying degrees of freedom. These facts will constrain every attempt to understand thermodynamics in gravitational systems. The importance of entropy lies not in metaphor, but in precision. It provides a bridge between microscopic law and macroscopic behavior. It explains the arrow of time without introducing new dynamics. It transforms thermodynamics from a phenomenological science into a statistical one. Only with this foundation in place can the tension between gravity and thermodynamics be understood. Gravity appears time-symmetric, yet gravitational systems evolve irreversibly. Entropy governs time, while gravity governs structure. Bringing these together will require careful attention to what entropy truly measures and what it demands of any physical theory. The statistical interpretation of entropy also explains why macroscopic laws appear so rigid, even though they rest on probability. When a system contains an enormous number of microscopic constituents, the difference between likely and unlikely outcomes becomes extreme. The number of microstates corresponding to high-entropy macrostates exceeds those of low-entropy macrostates by factors that grow exponentially with system size. As a result, entropy increase is not merely probable, but effectively guaranteed. Macroscopic behavior becomes predictable because deviations are suppressed by overwhelming statistics. This suppression does not rely on ignorance in a psychological sense. It is a structural feature of large systems. Even if the microscopic state were known perfectly, the overwhelming majority of trajectories consistent with the laws of motion would still lead toward higher entropy macrostates. The arrow of time emerges from combinatorics rather than from incomplete knowledge alone. This insight dissolves another common confusion. Entropy increase does not require energy dissipation or friction. It does not depend on imperfections or noise, even perfectly reversible. Microscopic dynamics produce irreversible macroscopic behavior once coarse graining is introduced. Coarse graining is not an approximation of convenience. It reflects the fact that macroscopic descriptions cannot track microscopic detail. The role of coarse graining is central. A macrostate groups together many microstates by ignoring distinctions that are irrelevant at large scales. Entropy depends on how this grouping is performed. Change the variables that define the macrostate and the entropy changes. This does not make entropy subjective, it makes it relational. Entropy is defined relative to a chosen level of description grounded in physical accessibility. This relational character becomes critical later. In gravitational systems, the choice of coarse graining is not obvious. Horizons hide information. Observers lose access to regions of space-time. The definition of microstates becomes observer-dependent. Entropy acquires a geometric aspect because access to information is limited by space-time structure itself. Another essential feature of statistical entropy is that it applies equally to equilibrium and non-equilibrium situations. Entropy production occurs whenever a system evolves toward more probable macrostates. Equilibrium is not required. The second law describes a tendency, not a destination. Systems approach equilibrium because equilibrium corresponds to maximal entropy under fixed constraints. Constraints matter. Entropy does not increase without bound. It increases until it reaches the maximum allowed by energy volume and other conserved quantities. These constraints define the space of accessible microstates. Entropy counts how many of those microstates are compatible with the macrostate at hand. This structure clarifies why entropy is not simply disorder. Order and disorder are vague visual notions. Entropy is precise. A highly structured crystal at low temperature has low entropy because few microstates realize that structure. A turbulent fluid can have lower entropy than a uniform gas depending on constraints. Visual complexity is irrelevant. What matters is multiplicity. The statistical framework also explains fluctuations. Even in equilibrium, entropy can fluctuate downward temporarily. These fluctuations are allowed by the laws of motion. Their probability decreases exponentially with system size. For macroscopic systems, they are negligible. For small systems, they can be observed. This behavior has been confirmed experimentally. The second law is statistical, not absolute. Time symmetry at the microscopic level remains intact throughout. Every trajectory that increases entropy has a time-reversed counterpart that decreases entropy. The difference is not in what is allowed, but in what is likely. The arrow of time reflects the fact that the universe began in a low entropy state. Without that condition, entropy would not define a direction. This dependence on initial conditions is unavoidable. Statistical mechanics does not explain why the universe began in a low entropy state. It takes that fact as input. Once given, the arrow of time follows inevitably. Entropy increase is a consequence, not a cause. At this stage, entropy is fully defined as a physical quantity. It counts microstates. It measures missing information. It explains irreversibility without modifying fundamental laws. It depends on underlying degrees of freedom and on access to information. It is objective in its consequences and relational in its definition. These features will collide with gravity in a way that challenges intuition. Gravitational systems do not behave like gases in boxes. They clump rather than spread. Uniformity corresponds to low entropy rather than high. The statistical logic remains valid, but its application changes dramatically. Before addressing that collision, one conclusion must be fixed. Entropy is not disorder. It is not decay. It is not a force. It is a measure of possibility. It tells us which macrostates are typical given microscopic laws and constraints. Any attempt to understand gravity thermodynamically must respect this definition. The final element of the entropy framework concerns its relationship with time and with gravity specifically. Entropy does not merely describe states. It defines a temporal orientation. The direction in which entropy increases is what distinguishes future from past in macroscopic experience. This arrow is not written into the equations of motion. It arises because the universe began in a very special state, with extraordinarily low entropy. This low entropy beginning is not a minor detail, it is essential. If the universe had begun in a generic high entropy configuration, there would be no arrow of time. Macroscopic processes would show no preferred direction. Entropy increase is meaningful only relative to an initial condition that is highly constrained. The arrow of time therefore reflects a property of the universe as a whole rather than a feature of local dynamics. At first glance, gravity seems irrelevant to this story. Statistical mechanics treats gravity as just another interaction acting on particles. But this assumption fails once gravity becomes dominant. Gravitational systems behave in ways that reverse ordinary thermodynamic intuition. In non-gravitational systems, entropy increases as matter spreads out and energy disperses. With gravity, entropy increases as matter clumps and structure forms. This reversal is not a violation of thermodynamics. It is a consequence of how microstates are counted when gravity is long-range and attractive. A uniform distribution of matter in a gravitational system corresponds to a highly constrained macrostate. There are relatively few microscopic configurations that realize perfect uniformity. As gravity amplifies small fluctuations, the number of accessible microstates grows. Entropy increases even as visible structure emerges. This insight resolves a long-standing confusion in cosmology. The early universe was remarkably smooth and homogeneous. At first, this appears to be a state of high entropy. In fact, it was a state of extremely low gravitational entropy. Gravity had not yet produced structure. The smoothness of the early universe represents a highly special condition, not a generic one. As time progresses, gravity drives the universe away from this special state. Density fluctuations grow. Matter collapses into stars, galaxies, and clusters. Entropy increases because the number of microscopic configurations compatible with these macrostates increases. Complexity and entropy rise together. The arrow of time points towards structure formation rather than away from it. This behavior highlights a crucial distinction. Entropy is not tied to visual simplicity or complexity. It is tied to probability. Gravitational clumping is entropically favored, even though it produces intricate structures. The intuition built from gases in boxes fails because gravity changes the space of possibilities. The statistical logic remains intact. The same combinatorial reasoning applies. What changes is the definition of the macrostate and the relevant degrees of freedom. Gravity reshapes which configurations are typical. Uniformity becomes rare. Clumping becomes likely. This has profound implications. Gravity does not merely participate in thermodynamic evolution, it reshapes thermodynamics itself. The arrow of time is not generated by gravity, but gravity amplifies it dramatically once a low entropy initial condition is given. The universe evolves irreversibly because gravity drives it toward ever larger regions of configuration space. Importantly, gravity itself remains time-symmetric. The equations governing gravitational dynamics do not prefer expansion over contraction or collapse over dispersal. The irreversibility arises from statistics, not from force laws. The arrow of time is emergent even in gravitational systems. This separation must be maintained carefully. Gravity does not cause entropy increase in the same way that friction causes heating. Gravity reorganizes the space of microstates. It determines which macrostates are typical. Entropy increase remains a statement about probability and missing information. At this point, the tension becomes visible. Gravity is described by time-symmetric geometric equations. Entropy defines an arrow of time. Yet gravitational systems exhibit irreversible behavior on cosmic scales. The two descriptions coexist without contradiction, but without direct connection. Geometry alone does not explain entropy. Entropy alone does not explain geometry. This tension prepares the ground for what follows. When gravity becomes strong enough to produce horizons, entropy ceases to be merely a property of matter. It becomes associated with spacetime itself. The statistical framework developed here will be tested in the most extreme gravitational environments. The results will force entropy and geometry into direct contact. The lesson of this chapter is precise. Entropy measures missing information through microstate counting. Irreversibility emerges from probability, given a low entropy beginning. Gravity reshapes which macrostates are typical, and therefore reshapes entropy itself. None of these statements are speculative. They follow directly from established statistical physics applied carefully to gravitational systems. With entropy now understood in its full statistical meaning, the stage is set. Gravity will no longer be treated as a background interaction acting on thermodynamic systems. It will become the arena in which thermodynamics itself acquires new meaning. The arrow of time appears so deeply woven into experience that it is often mistaken for a fundamental feature of nature. Events unfold in one direction. Causes precede effects. Memories point toward the past and not the future. Yet when the laws that govern fundamental physics are examined, this directionality is nowhere to be found. The equations that describe motion fields and even space-time curvature remain valid whether time runs forward or backward. Gravity is no exception. In its geometric formulation, gravity is governed by equations that are exactly time-symmetric. A solution describing an expanding universe has a time-reversed counterpart describing a contracting one. A collapsing star and an uncollapsing star are equally valid mathematically. Nothing in the structure of the equations forbids reversal. Time asymmetry does not originate in gravitational law. This creates a conceptual tension. Gravitational systems in the real universe are profoundly irreversible. Stars form, ignite, exhaust their fuel, and collapse. Galaxies assemble hierarchically. Black holes grow through accretion and merger. None of these processes are observed to run backward. The universe evolves from simplicity toward complexity in a way that defines a clear temporal direction. The resolution lies not in gravity itself, but in entropy. As established earlier, irreversibility emerges statistically from low entropy initial conditions. Gravity does not violate this framework. It amplifies it. The early universe began in an extraordinarily special state. Matter and energy were distributed with remarkable uniformity. Density fluctuations were tiny. From a gravitational perspective, this configuration corresponds to extremely low entropy. This statement may appear counterintuitive. Uniformity is often associated with equilibrium and high entropy in non-gravitational systems. With gravity, the logic is reversed. A smooth distribution of matter is unstable and highly constrained. There are relatively few microscopic configurations that realize such uniformity once gravity is taken into account. The overwhelming majority of configurations correspond to clumped structures. As time progresses, gravity drives the universe away from this special initial condition. Small fluctuations grow, matter collapses, structure forms. Entropy increases because the number of accessible microstates increases dramatically. The arrow of time points away from uniformity and toward structure. Importantly, this arrow is not encoded in gravitational dynamics. It is imposed by the initial condition. Gravity simply responds to that condition. It does not choose a direction. It accelerates entropy increase once evolution begins. This distinction matters because it separates explanation from description. Gravity describes how matter moves given a space-time geometry. Entropy explains why the universe evolves irreversibly given its starting point. Confusing the two leads to false paradoxes. Gravity does not generate the arrow of time. it operates within it. The interplay becomes more subtle when self-gravitating systems are examined in isolation. Such systems exhibit negative heat capacity. As they lose energy, they become hotter. This behavior violates ordinary thermodynamic intuition, but not thermodynamics itself. It reflects the fact that energy cannot be localized cleanly in gravitational systems. Entropy accounting becomes global rather than local. These features signal that gravity reshapes thermodynamic reasoning without undermining it. The second law remains valid. Entropy still increases. What changes is the definition of typical states. Gravity alters which macrostates dominate the space of possibilities. At this stage, the relationship between gravity and entropy remains indirect. Gravity governs motion and structure. Entropy governs probability and time. The two coexist, but are not yet unified. Geometry does not explain entropy. Entropy does not explain geometry. This separation will not survive further scrutiny. In the presence of horizons, entropy becomes inseparable from spacetime itself. The arrow of time and the structure of spacetime begin to intersect directly. To see this intersection clearly, gravity must be pushed to its most extreme limits. The role of initial conditions now becomes unavoidable. For entropy to increase, the universe must begin in a state that is extraordinarily atypical. From a statistical perspective, almost all possible configurations of matter and energy correspond to high entropy. The early universe was not in such a state. It was smooth, homogeneous, and nearly isotropic across vast distances. This configuration occupies an extremely small region of the space of all possible gravitational microstates. Gravity is crucial here because it determines what counts as typical. In a non-gravitational gas, equilibrium corresponds to uniformity. With gravity, equilibrium corresponds to collapse. A universe filled with black holes would have far higher entropy than a smooth expanding cosmos. The early universe, therefore, did not begin near equilibrium. It began far from it. The arrow of time is rooted in this fact. This observation shifts the mystery rather than resolving it. Statistical physics explains why entropy increases once a low entropy beginning is given. It does not explain why such a beginning occurred. The low entropy of the early universe is not predicted by known laws. It is an empirical fact. Gravity magnifies its consequences but does not explain its origin. As the universe evolves, gravity converts this low entropy condition into a cascade of irreversible processes. Matter falls into potential wells. Gas clouds collapse. Stars ignite. Nuclear burning proceeds until fuel is exhausted. Remnants form. Each step increases entropy by opening access to vastly larger sets of microstates. Gravity does not violate the second law. It drives it forward on cosmic scales. The arrow of time therefore aligns with structure formation. This alignment is not accidental. It reflects the statistical dominance of clumped configurations in a gravitationally interacting system. The universe evolves towards states that are more probable given the presence of gravity. These states appear ordered to human observers, but they are entropically favored. This reasoning clarifies a subtle point. The growth of structure does not contradict entropy increase. It exemplifies it. Order and entropy are not opposites. Entropy measures multiplicity, not appearance. A galaxy contains enormous entropy despite its apparent organization because there are countless microscopic arrangements compatible with its macroscopic form. The time symmetry of gravitational equations remains intact throughout. For every history in which structure forms, there exists a mathematically valid history in which structure dissolves. The difference lies not in possibility, but in probability. The universe follows the overwhelmingly likely path away from its special beginning. This distinction becomes especially clear in cosmology. The expansion of the universe does not itself define the arrow of time. A contracting universe could also exhibit entropy increase. What matters is not expansion, but initial entropy. Gravity then shapes how entropy grows. At this point, gravity appears as a catalyst rather than a cause. It accelerates entropy increase once conditions are set. It does not encode irreversibility into the laws themselves. This separation preserves consistency. Gravity remains time-symmetric. Thermodynamics remains statistical. Yet the relationship is no longer loose. Gravity determines which configurations are probable. It shapes the entropy landscape. The arrow of time is not independent of gravity. It is amplified by it. The two are intertwined even if not unified. This entanglement becomes unavoidable when horizons enter the picture. Horizons limit access to information. They introduce observer-dependent boundaries. Entropy ceases to be a property of matter alone. It becomes tied to space-time structure. When that happens, the arrow of time can no longer be discussed without reference to geometry. The arrow of time therefore prepares the ground. It reveals a mismatch between time-symmetric laws and irreversible behavior. It shows that gravity reshapes thermodynamics without generating it. It exposes the limits of purely geometric explanations. The next step will push gravity into regimes where entropy is no longer optional but mandatory. The final clarification concerns what gravity contributes and what it does not. Gravity does not insert irreversibility into the fundamental equations. It does not encode a preferred temporal direction into spacetime geometry. Any attempt to locate the arrow of time directly in curvature fails. The equations allow evolution in both directions equally. What gravity does is reshape the space of possibilities so dramatically that one direction becomes overwhelmingly favored once a low entropy condition is given. This reshaping has concrete thermodynamic consequences. Self-gravitating systems behave unlike ordinary systems because energy cannot be confined without altering space-time structure. As matter collapses, gravitational potential energy is converted into kinetic energy and radiation. The system heats up even as it loses energy. This negative heat capacity is not a pathology. It is a signature of long-range interaction and universal coupling. It reveals that local thermodynamic reasoning breaks down in gravitational contexts. Because of this breakdown, entropy accounting becomes global. One cannot isolate a subsystem cleanly and ignore the rest of the universe. Radiation escapes, horizons form. Information becomes inaccessible. Entropy is no longer merely a count of particle configurations. It becomes sensitive to geometry and causal structure. This sensitivity exposes the limits of classical reasoning. In ordinary, thermodynamics entropy increase can be understood without reference to space-time structure. In gravitational systems, space-time itself determines which degrees of freedom are accessible. An observer outside a horizon cannot count microstates inside it. Entropy becomes observer-dependent. This dependence is not subjective. It is imposed by causal structure. At this stage, a critical distinction must be maintained. Gravity reshapes entropy, but does not redefine it. Entropy remains a measure of missing information. What changes is what information is missing and why. Horizons enforce ignorance by geometry rather than by coarse graining. Spacetime itself limits access to microstates. This is the point at which the separation between gravity and thermodynamics collapses. Once horizons exist, entropy is no longer optional. It must be assigned for consistency. Processes that reduce total entropy become forbidden. The laws of thermodynamics apply even when the system is purely gravitational. The arrow of time therefore acquires a new layer. It is still rooted in initial conditions and probability, but it is now enforced by space-time structure. Gravity does not merely amplify entropy increase, it enforces it through causal boundaries. The universe cannot evolve in a way that violates entropy bounds without contradicting gravitational dynamics. This enforcement does not require new laws. It emerges from the combination of geometry and information. Space-time responds to energy in a way that preserves thermodynamic consistency. When energy concentration threatens entropy bounds, horizons form. Geometry intervenes to protect the second law. This behavior is not speculative. It is encoded in classical solutions of general relativity and becomes unavoidable once quantum effects are included. Gravity appears to know about entropy, even though entropy is not written into the equations explicitly. The consistency between geometry and thermodynamics is too precise to be accidental. At this point, the arrow of time is no longer a purely statistical curiosity. It becomes a structural feature of gravitational systems. Not because gravity breaks time symmetry, but because gravity enforces information constraints that make entropy decrease physically inaccessible. This realization marks the transition. The arrow of time can no longer be discussed without reference to space-time. Gravity can no longer be discussed without reference to entropy. The two are linked by information. The next step follows naturally. If space-time enforces entropy bounds, then space-time itself must carry entropy. Geometry must encode information capacity. This idea will move entropy from matter to space-time and force a rethinking of what geometry actually represents. Black holes enter gravitational physics not as speculative objects, but as exact consequences of general relativity. When matter is compressed beyond a critical threshold, space-time curvature becomes so extreme that a boundary forms separating regions of causal contact from regions forever hidden. This boundary is called the event horizon. From the outside, a black hole is remarkably simple. It is fully characterized by a small set of macroscopic quantities, such as total mass angular momentum and electric charge. All other details of the matter that formed it are erased from observable description. At first, this simplicity appears to clash violently with thermodynamics. Ordinary physical systems carry enormous microscopic complexity. A star, a gas cloud, or a planet can exist in an astronomical number of internal configurations. When such matter collapses into a black hole, all of that complexity disappears behind the horizon. The external description loses access to the microscopic information. If entropy measures missing information, then black hole formation seems to destroy entropy rather than increase it. This would violate the second law of thermodynamics in its most basic form. The paradox is sharpened by classical gravity itself. In general relativity, nothing escapes from within the event horizon. Once information crosses that boundary, it is permanently inaccessible to outside observers. If matter with entropy falls into a black hole and leaves no trace behind, then total entropy visible to the universe decreases. Classical geometry appears to permit a direct violation of thermodynamic law. The resolution begins with a discovery that initially seems almost accidental. Certain properties of black holes obey mathematical relations that mirror the laws of thermodynamics with extraordinary precision. These are not loose analogies. They are exact theorems derived directly from the equations of general relativity. The most striking of these is the area theorem. In any classical process, the total area of black hole horizons never decreases. This behavior mirrors the second law of thermodynamics. Entropy never decreases in an isolated system. When two black holes merge, the area of the resulting horizon is greater than or equal to the sum of the original areas. No classical process allows horizon area to shrink. The resemblance is too exact to ignore. Additional parallels follow. Black holes respond to changes in mass and rotation in a way analogous to energy exchange and work. The surface gravity of a black hole behaves like temperature in thermodynamic relations. These results are derived rigorously. They are not motivated by intuition about heat or molecules. They emerge from the structure of space-time geometry itself. At this stage, the resemblance remains formal. Classical black holes do not radiate. They absorb matter and energy, but emit nothing. Without radiation, there is no physical temperature, and without temperature, entropy remains an abstract label rather than a measurable quantity. The analogy with thermodynamics is suggestive but incomplete. The decisive step comes from quantum theory. When quantum fields are considered in curved spacetime, black holes are no longer perfectly black. Vacuum fluctuations near the horizon lead to the emission of radiation. This radiation has a precise thermal spectrum, characterized by a temperature inversely proportional to the mass of the black hole. The result is unavoidable. It follows from quantum field theory applied to curved geometry. This radiation causes black holes to lose mass over time. They evaporate slowly by emitting energy. The process is extremely weak for astrophysical black holes, but its theoretical existence is secure. Multiple independent derivations converge on the same conclusion. Black holes have a genuine physical temperature. Once temperature is established, entropy becomes physical. The formal resemblance becomes a real thermodynamic identity. Black holes obey the laws of thermodynamics exactly. Their entropy is proportional to the area of the event horizon. This entropy is enormous. A black hole of stellar mass carries far more entropy than all the ordinary matter that formed it. This result is not an analogy. It is a calculated consequence of combining general relativity quantum field theory and statistical reasoning. The proportionality constant is fixed by fundamental constants. There is no freedom to adjust it. The entropy-area relation is rigid. The implication is profound. Entropy is no longer confined to matter and radiation. It is associated with space-time itself. The event horizon is not merely a geometric boundary. It carries entropy and temperature. Thermodynamics is no longer applied to gravity by comparison. It is built into gravitational systems at a fundamental level. This realization transforms the role of black holes. They are no longer pathological curiosities. They become laboratories where gravity thermodynamics and quantum theory intersect with unavoidable consequences. Any theory of gravity that claims to be fundamental must reproduce these results exactly. At the same time, caution is required. The existence of black hole entropy does not explain what the entropy counts. It establishes that something is being counted. The microscopic degrees of freedom responsible for this entropy are not identified by classical geometry. The result points beyond the geometric description without specifying what lies beneath. Black hole thermodynamics therefore occupies a precise position. It is fully established theoretically. It follows from rigorous calculations, yet it exposes a gap in understanding. Space-time behaves as if it carries microscopic information, while appearing smooth and featureless in classical description. This gap will not close by modifying thermodynamics or geometry alone. It signals that gravity has a thermodynamic aspect that geometry by itself does not explain. Entropy has moved from matter to space-time. The next step will examine what this implies about the structure of space-time itself. The appearance of entropy in black holes immediately raises a question that cannot be avoided. Entropy is not an abstract label. It counts microscopic possibilities. For gases, it counts particle arrangements. For radiation, it counts field modes. For black holes, there is no such account within classical gravity. The space-time outside the horizon is smooth. The space-time inside is hidden. Yet the entropy is enormous. Something real is being counted, and classical geometry does not reveal what it is. The scale of the entropy makes this problem sharper. A black hole with the mass of the Sun has an entropy vastly larger than that of a star made of ordinary matter with the same mass. When a star collapses into a black hole, entropy increases by an enormous factor. This increase is not supplied by additional matter or radiation. It is supplied by gravity itself. The entropy is carried by the horizon. Even more striking is how this entropy scales. In ordinary thermodynamic systems, entropy grows with volume. The more space available, the more microscopic configurations are possible. For black holes, entropy grows with area. The entropy is proportional to the surface of the horizon rather than the volume it encloses. This behavior has no analog in non-gravitational physics. It cannot be explained by conventional statistical mechanics. The area scaling is not an accident of dimensional analysis. It survives detailed calculation. The numerical coefficient is fixed. The result is robust under changes in the black hole parameters. Whether the black hole is rotating charged or non-rotating, the entropy always scales with horizon area. The universality of this law demands explanation. This behavior suggests that the degrees of freedom responsible for black hole entropy are not distributed throughout space in the usual way. They appear to be associated with the horizon itself. The horizon acts as an information boundary. It separates what can be known from what cannot. Entropy counts the number of distinct ways that boundary can encode information while remaining consistent with the same macroscopic geometry. At this point, a crucial constraint must be emphasized. None of these results identify the nature of the microscopic degrees of freedom. They do not tell us whether the microstates reside on the horizon or whether they are non-local. They do not tell us whether spacetime is discrete or continuous at the smallest scales. The calculations remain silent on these questions. This silence is not a weakness, it is a feature. The entropy area law is derived without committing to a specific microscopic model. It relies only on consistency between gravity quantum theory and thermodynamics. Any viable microscopic theory must reproduce this result. The entropy is fixed. The microstates are constrained even if their identity is unknown. Another implication follows directly. If black hole entropy is real, then entropy is not merely a bookkeeping device for matter. It is a property of space-time geometry under certain conditions. The horizon is not passive. It carries thermodynamic attributes. Space-time itself participates in entropy accounting. This realization forces a change in perspective. Geometry can no longer be regarded as a purely kinematic structure. It has thermodynamic content. It behaves as if it possesses internal degrees of freedom that can store information and exchange energy. Classical general relativity does not describe these degrees of freedom. It averages over them. The thermodynamic laws obeyed by black holes are not optional. They constrain all physical processes involving gravity. Any process that would reduce total entropy, including horizon entropy, is forbidden. This requirement applies even when no ordinary matter is involved. Purely gravitational processes must respect the second law. This constraint explains why horizon area cannot decrease in classical gravity. It also explains why horizons form when energy is concentrated beyond certain limits. Geometry responds in a way that protects thermodynamic consistency. Space-time intervenes to prevent violations of entropy bounds. The black hole therefore becomes more than an object. It becomes a principle. It shows that gravity enforces information limits. It reveals that space-time geometry knows about entropy, even though entropy is not explicit in the equations. The agreement between geometry and thermodynamics is too precise to be coincidental. At the same time, restraint remains essential. Black hole thermodynamics does not prove that gravity is emergent. It does not prove that space-time is made of microscopic constituents analogous to atoms. It establishes that space-time behaves as if it has such constituents. Behavior and ontology must not be conflated. What black holes provide is a controlled environment where the interplay between gravity entropy and quantum theory becomes unavoidable. They eliminate interpretations that deny entropy a fundamental role in gravity. They force any deeper theory to account for information storage and processing by space-time. The conclusion is narrow but powerful. Gravity is not thermodynamically inert. Space-time carries entropy. Horizons are thermodynamic objects. These statements are not speculative. They follow directly from established physics. Any attempt to understand gravity at a deeper level must begin here. This realization sets the direction forward. If space-time carries entropy, then space-time must have microscopic degrees of freedom. If those degrees of freedom exist, then geometry cannot be fundamental in the same sense classical descriptions assume. The next step will examine entropy as a property of space-time itself, rather than of particular objects. The final consequence follows from consistency rather than speculation. If black holes obey genuine thermodynamic laws, then space-time itself cannot be excluded from thermodynamic accounting. Entropy is not an optional label that can be assigned or removed at will. It constrains physical evolution. Processes that would reduce total entropy are forbidden regardless of whether the system contains ordinary matter or only gravity. Spacetime must therefore participate in thermodynamics at a fundamental level. This participation changes the role of geometry. Geometry is no longer merely a description of distances and trajectories. In the presence of horizons, geometry carries entropy, temperature, and energy exchange. These quantities are not metaphors. They are defined operationally and enter physical laws in the same way they do for ordinary systems. The horizon behaves like a thermodynamic object. Yet nothing in the classical description of spacetime explains this behavior. A smooth continuum with no internal structure cannot store information. It cannot have microstates. It cannot possess entropy in the statistical sense. The fact that spacetime does possess entropy implies that the smooth geometric description must be incomplete. It must be an effective description that hides microscopic detail. This conclusion is not optional. Entropy cannot exist without degrees of freedom. The area law fixes how many degrees of freedom must exist per unit area. Any microscopic theory of gravity must reproduce this number exactly. There is no freedom to adjust it. Black hole entropy is quantitative, not qualitative. At the same time, nothing in black hole thermodynamics tells us what the microscopic degrees of freedom are. They may not resemble particles or fields. They may not live at points in space-time. They may not be local in any conventional sense. The calculations do not decide this. They impose constraints without revealing mechanisms. This restraint is critical. Black hole thermodynamics does not claim to explain gravity. It exposes a boundary beyond which classical explanations fail. It tells us that space-time behaves thermodynamically. It does not tell us why. Any attempt to go further must introduce new conceptual tools while preserving established results. The significance of black holes lies precisely here. They force thermodynamics into gravity without ambiguity. They show that entropy and geometry are inseparable under extreme conditions. They eliminate interpretations in which gravity is purely geometric and information free. Spacetime must encode information. At the same time, the conclusions must not be overstated. Black hole entropy does not by itself prove that gravity is emergent. It does not prove that spacetime is made of discrete elements. It establishes that classical geometry cannot be the final description. Whether the underlying structure is fundamental or emergent remains open. What black holes provide is a non-negotiable constraint. Any theory of gravity that claims to be fundamental must reproduce black hole thermodynamics. Exactly. It must explain why entropy scales with area. It must explain why horizons carry temperature. It must explain how information is stored and preserved. This requirement narrows the space of viable theories dramatically. Geometry alone is not enough. Thermodynamics alone is not enough. The two must be unified in a way that respects both. The path forward therefore becomes clear. If spacetime carries entropy, then spacetime itself must be treated as a thermodynamic system. Understanding gravity will require understanding how geometry emerges from information and statistics, or how information is encoded in geometry at a deeper level. Black hole thermodynamics does not end the story. It begins it. It marks the point where gravity can no longer be discussed without entropy, and entropy can no longer be discussed without spacetime. The next step will generalize this insight beyond black holes and ask whether entropy is a universal property of spacetime itself. Once entropy is firmly established as a real physical property of black holes, its significance can no longer be confined to those objects alone. The defining feature of black hole entropy is not collapse or singularity, but the existence of a horizon. The horizon marks a boundary beyond which information is inaccessible to a given observer. This shift in emphasis changes the question fundamentally. The issue is no longer what happens inside a black hole, but what happens whenever spacetime restricts access to information. A horizon is not an exotic feature limited to extreme astrophysical objects. Horizons appear whenever spacetime geometry prevents an observer from receiving signals from certain regions. An accelerating observer in otherwise empty space perceives a horizon. An observer in an expanding universe encounters a cosmological horizon. In each case, the observer loses access to part of space-time. In each case, thermodynamic behavior appears. Temperature and entropy are assigned consistently. This pattern is not accidental. Entropy appears wherever information is hidden by space-time itself. The entropy does not depend on the detailed composition of matter. It depends only on geometry and causal structure. This universality is decisive. It implies that entropy is a property of space-time rather than of particular objects embedded within it. The entropy associated with horizons scales with area. This result is deeply non-trivial. In every non-gravitational system, entropy scales with volume because degrees of freedom are assumed to fill space. Area scaling contradicts that assumption. It implies that the fundamental degrees of freedom relevant to gravity do not reside throughout the bulk in the usual way. Instead, the maximum information content of a region is determined by its boundary. This conclusion forces a revision of long-held intuition. In ordinary physics, the number of degrees of freedom increases with the size of the region considered. In gravitational systems, this is no longer true. Adding energy to a region beyond a certain point does not increase the number of accessible states. It produces a horizon. Geometry intervenes to limit information. This limit is not imposed externally. It arises dynamically from gravitational collapse. When too much energy is packed into a region, space-time responds by forming a boundary that hides information. Entropy does not grow without bound. It saturates at a value proportional to area. This behavior is universal and independent of microscopic detail. Importantly, this result does not depend on knowing what the microscopic degrees of freedom are. The entropy can be calculated without specifying their nature. The calculation relies on consistency between gravity quantum theory and thermodynamics. The absence of a microscopic model does not weaken the conclusion. It strengthens it. Whatever space-time is made of it must reproduce the entropy-area relationship exactly. This establishes a critical constraint. Space-time cannot be a featureless continuum at all scales. A continuum has infinitely many degrees of freedom per unit volume. If space-time were truly continuous at arbitrarily small scales, entropy would diverge. The fact that entropy is finite and proportional to area implies that the number of degrees of freedom is finite and bounded. At the same time, caution is required. Finite does not necessarily mean discrete in a simple sense. The underlying structure may not resemble a lattice or a collection of particles. The result tells us that space-time has limited information capacity. It does not tell us how that capacity is implemented. Another implication follows directly. If entropy is associated with horizons, then entropy becomes observer-dependent. Different observers have access to different regions of space-time and therefore assign different entropies. This dependence is not subjective. It is enforced by causal structure. What an observer cannot in principle access cannot be counted. This observer dependence does not undermine objectivity. The laws governing entropy assignment are precise and universal. Given an observer and a horizon, the entropy is fixed. The dependence reflects physical limitation, not ambiguity. Space-time itself defines what information is available. This shift has profound consequences. Entropy is no longer a global property of matter distribution alone. It becomes a relational property involving space-time geometry and observers. Thermodynamics acquires a geometric component. Information loss is enforced by causal structure rather than by coarse graining. At this stage, the classical geometric description reaches its limit. Geometry predicts horizons, but does not explain their entropy. It specifies causal boundaries, but does not assign information capacity. The thermodynamic behavior of spacetime cannot be derived from geometry alone. Something deeper must underlie both. The conclusion must remain restrained. The existence of spacetime entropy does not identify the microscopic degrees of freedom. It does not prove that spacetime is emergent. It does not specify a unique underlying theory. It establishes that any such theory must account for entropy area scaling and information bounds. What has changed is the status of spacetime. It is no longer merely the arena in which thermodynamic processes occur. It is a thermodynamic system in its own right. Geometry summarizes behavior that reflects hidden degrees of freedom and information constraints. This realization transforms the problem of gravity. The question is no longer how spacetime curves, but why spacetime has entropy at all. Answering that question requires treating information as fundamental rather than auxiliary. Entropy has moved from matter to spacetime. Information has become inseparable from geometry. Any attempt to understand gravity at a deeper level must now explain how spacetime stores information and why its capacity is bounded by area. This sets the stage for the next problem. If spacetime carries entropy and information, then those quantities must obey the rules of quantum mechanics. Information must be conserved. This requirement will collide directly with classical geometry and expose a tension that cannot be resolved without new principles. The area scaling of spacetime entropy imposes a severe restriction on how information can be organized in gravitational systems. If entropy measures missing information, then an area bound means that information capacity is fundamentally limited by geometry. No physical process can encode more independent information inside a region than allowed by the surface that encloses it. This is not a practical limitation. It is enforced by gravitational dynamics themselves. This constraint directly contradicts the assumptions of ordinary quantum field theory. In a non-gravitational setting, each point in space is treated as an independent carrier of degrees of freedom. Entropy therefore grows with volume. Gravity forbids this picture. If independent degrees of freedom truly filled space at arbitrarily small scales, the entropy inside a region would scale with volume and quickly exceed the area bound. Spacetime would collapse under its own informational weight. The fact that this does not happen means that the local field description must be incomplete when gravity is present. Degrees of freedom cannot be independent in the way ordinary field theory assumes. They must be correlated or constrained in a way that dramatically reduces the number of accessible states. Geometry enforces these correlations by limiting information through horizon formation. This enforcement is not subtle. Attempts to concentrate too much energy or information into a region trigger gravitational collapse. A horizon forms. Information that would otherwise increase entropy becomes inaccessible. The system reorganizes itself to respect the area bound. Spacetime acts as a regulator that protects thermodynamic consistency. The universality of this behavior is striking. The entropy bound does not depend on the type of matter involved or on the detailed dynamics. It applies to all physical systems equally. Whether the information is carried by particles, fields, or radiation, the limit is the same. Geometry alone determines the maximum entropy. This universality suggests that the entropy bound reflects a fundamental feature of spacetime rather than an emergent property of particular matter configurations. Spacetime itself appears to encode information limits in its structure. Entropy becomes a geometric quantity in the same sense that distance and duration are geometric quantities. At the same time, the result must not be misinterpreted. The area bound does not imply that information literally lives on surfaces in a simple physical sense. It implies that the number of independent degrees of freedom accessible within a region is proportional to area. How those degrees of freedom are realized remains unknown. The bound constrains theories without specifying mechanisms. This distinction is essential. The entropy bound is a statement about capacity, not location. It tells us how much information can be stored, not where it is stored. The underlying degrees of freedom may be highly non-local. They may not correspond to points or surfaces in spacetime at all. Geometry may be a derived description of how information is organized rather than a container for it. Another consequence follows from observer dependence. Because entropy is associated with horizons, different observers assign different entropies to the same spacetime. An observer with access to a larger region counts more microstates than one restricted by a horizon. This difference is not subjective. It reflects physical access enforced by causal structure. Information that cannot be accessed cannot be counted. This observer dependence reinforces the informational interpretation. Entropy depends not only on physical configuration, but on what can be known. Space-time geometry determines knowledge limits. Thermodynamics becomes inseparable from causal structure. At this stage, geometry appears increasingly like an effective description. It tracks information capacity and access rather than fundamental constituents. Curvature tells us how space-time responds to energy. Entropy tells us how space-time limits information. Both describe macroscopic behavior. Neither reveals microscopic detail. This perspective narrows the possibilities for any deeper theory. Whatever the fundamental description may be, it must explain why information is bounded by area and why geometry enforces that bound dynamically. It must reproduce space-time entropy without contradiction. It must respect observer-dependent horizons and information limits. The classical picture of space-time as a smooth continuum filled with local degrees of freedom cannot satisfy these requirements. It overcounts information. It ignores entropy, bounds. It treats geometry as fundamental when its behavior suggests otherwise. What emerges instead is a picture in which space-time behaves like a thermodynamic system with a finite information capacity. Geometry summarizes how that capacity responds to energy and motion. Curvature becomes a macroscopic variable rather than a microscopic one. This conclusion does not resolve the nature of space-time. It constrains it. It tells us that any successful theory must treat information as fundamental and geometry as secondary. The next step will examine how information conservation in quantum mechanics collides with classical space-time and forces further revision. The final implication follows directly from the existence of space-time entropy and information bounds. If entropy is finite and proportional to area, then space-time must possess a finite number of microscopic degrees of freedom per unit area. Entropy cannot be defined without something to count. A perfectly smooth continuum with infinitely many independent degrees of freedom cannot satisfy this requirement. Classical geometry must therefore be an approximation that emerges when those microscopic degrees of freedom are coarse-grained. This conclusion is tightly constrained. The entropy-area relationship fixes the density of degrees of freedom precisely. Any microscopic theory must reproduce this value without adjustment. There is no freedom to rescale or reinterpret it. Space-time entropy is quantitative and exact. It does not tolerate ambiguity. At the same time, the nature of these degrees of freedom remains unknown. They may not resemble particles, fields, or strings. They may not live at points in space-time. They may be inherently non-local. The entropy calculation does not reveal their identity. It establishes only that they must exist and that their collective behavior gives rise to smooth geometry at large scales. This restraint is essential. Many speculative interpretations fail by overclaiming. Space-time. Entropy does not tell us what space-time is made of. It tells us that space-time has limited information capacity. The distinction between capacity and constitution must be maintained carefully. What is clear is that geometry alone cannot be fundamental. Curvature behaves like a thermodynamic variable. It responds to energy and information in a way that enforces entropy bounds. It summarizes collective behavior without exposing microscopic detail. In this sense, geometry plays a role similar to pressure or temperature in ordinary thermodynamics. This analogy does not trivialize geometry. Pressure and temperature are precise and predictive quantities, even though they are emergent. Geometry retains its precision, even if it is emergent. The success of general relativity is not diminished. It is explained. Geometry works because it captures the large-scale behavior of underlying degrees of freedom efficiently. This perspective also clarifies why gravity resists direct quantization. If curvature is not a fundamental variable but a macroscopic one, then attempts to quantize it directly may be misguided. Quantizing pressure does not reveal the atoms of a gas. Quantizing curvature may not reveal the microstructure of spacetime. The difficulty may be conceptual rather than technical. At this stage, gravity appears to occupy a unique position. It behaves classically at large scales. It carries entropy and temperature in the presence of horizons. It enforces information bounds. It responds to energy in a way consistent with thermodynamics. These features align naturally if spacetime has microscopic degrees of freedom whose collective behavior appears geometric. Yet restraint remains essential. None of this proves that spacetime is emergent in the same sense that thermodynamic variables are emergent from atoms. It proves that spacetime behaves as if it were. Behavior and ontology must not be conflated. The evidence constrains possibilities without selecting a final answer. The significance of spacetime entropy lies in what it forbids. It forbids interpretations in which spacetime is a featureless continuum with unlimited information capacity. It forbids theories that ignore information conservation. It forbids descriptions of gravity that treat entropy as accidental or auxiliary. What remains is a narrowed landscape. Spacetime must encode information. Geometry must reflect information limits. Gravity must be compatible with thermodynamics and quantum principles simultaneously. Any deeper theory must explain these facts without discarding the successes of general relativity. This realization completes the transition. Entropy has moved from matter to spacetime. Information has become a central organizing principle. Geometry has become a macroscopic descriptor rather than an unquestioned foundation. The next step will bring quantum mechanics fully into the discussion. If spacetime carries information, then that information must obey quantum rules. Information cannot be destroyed. This requirement will collide with classical horizons and force a reconsideration of how spacetime stores and releases information. Quantum mechanics introduces a principle that is both simple and unforgiving. Physical evolution preserves information. The complete microscopic state of a system at one moment determines the complete microscopic state at any other moment through unitary evolution. Information may be dispersed, hidden, or scrambled beyond practical recovery, but it cannot be destroyed. This requirement is not an interpretation. It is built directly into the mathematical structure of quantum theory. This principle collides violently with classical descriptions of black holes. In general relativity, a black hole forms a horizon that permanently hides whatever crosses it. Matter carrying enormous microscopic detail falls inward and becomes causally disconnected from the outside universe. From the external perspective, all that remains is mass rotation and charge. The microscopic information appears to vanish from observable reality. The conflict becomes unavoidable once black hole thermodynamics is taken seriously. Black holes radiate. They lose mass. Over extremely long times, they evaporate completely. If the radiation emitted during this process is purely thermal, then it carries no information about the material that formed the black hole. When evaporation finishes, nothing remains. Information would be irretrievably lost. This outcome is incompatible with quantum mechanics. Information loss would break unitarity. It would undermine predictability at the most fundamental level. The probabilistic interpretation of quantum theory would collapse. The conflict is not philosophical. It is mathematical and precise. This tension is known as the black hole information problem. It arises directly from combining three established facts. Horizons hide information. Black holes radiate thermally. Quantum evolution preserves information. All three are independently supported. Taken together, they cannot all be true in their naive forms. The force of the problem lies in its clarity. There is no experimental loophole and no interpretive ambiguity. Either information escapes from black holes in a subtle way, or one of the foundational principles must be revised. The classical picture of space-time geometry cannot remain unchanged. Over several decades, a broad theoretical consensus has emerged. Most physicists now believe that information is not destroyed by black holes. Instead, it must be encoded in correlations within the radiation, or stored in degrees of freedom associated with space-time itself. The radiation is not exactly thermal. It carries information in ways that are invisible to coarse observation, but present in principle. This conclusion is not based on direct experimental evidence. It is based on consistency. Allowing information loss would require abandoning quantum mechanics or radically altering it. The cost is too high. Preserving unitarity demands that space-time and gravity accommodate information conservation. This requirement reshapes the meaning of black hole, entropy. Entropy can no longer be interpreted merely as ignorance of inaccessible interior states. It must correspond to real microscopic degrees of freedom capable of encoding information and evolving unitarily. Entropy counts actual states, not bookkeeping artifacts. Once this step is taken, the classical picture of a smooth horizon becomes untenable. A perfectly featureless boundary cannot store information. If information is preserved, then the horizon must possess structure beyond what classical geometry describes. Space-time must carry degrees of freedom that are invisible at the classical level. It is essential to emphasize restraint. This conclusion does not identify the microscopic mechanism by which information escapes. It does not specify whether information is stored on the horizon spread throughout space-time or encoded non-locally. Different theoretical approaches propose different answers. What unites them is the rejection of fundamental information loss. The information problem therefore acts as a filter. It eliminates entire classes of theories that allow information destruction. It does not select a unique solution. It constrains the space of viable descriptions. Any acceptable theory of gravity must reconcile horizons, entropy, and unitarity. This constraint extends beyond black holes. If information is conserved in the presence of horizons, then all horizons must encode information. The issue is not limited to rare astrophysical objects. It applies to space-time itself, wherever causal boundaries appear. At this point, information becomes inseparable from gravity. Geometry alone cannot account for information storage and retrieval. Space-time must possess quantum properties that classical geometry averages over. The information problem does not merely challenge black hole physics. It challenges the classical conception of space-time. The significance of this realization is structural. Information is not an emergent convenience. It is a fundamental constraint. Gravity must respect it. Any attempt to understand space-time without accounting for information conservation is incomplete. This realization sets the direction forward. If space-time encodes information, then geometry may reflect how that information is organized rather than being fundamental itself. The next step is to understand how information capacity relates to geometry in a universal way. The demand that information be preserved imposes strict constraints on the structure of space-time. If information cannot be destroyed, then it cannot simply disappear behind a horizon forever. A horizon cannot be a one-way sink for information in a fundamental theory. It must possess degrees of freedom that can store information and later release it in a way consistent with unitary evolution. This requirement forces a reinterpretation of black hole evaporation. The radiation emitted by a black hole cannot be exactly thermal. Perfectly thermal radiation carries no information. Instead, the radiation must contain subtle correlations that encode the information of what fell into the black hole. These correlations are extraordinarily difficult to detect, but they are required in principle. Information is not lost. It is scrambled. This scrambling is not arbitrary. It must preserve the total information content while respecting the thermodynamic properties of the black hole. The radiation must appear thermal at coarse scales while remaining informationally complete at fine scales. This dual requirement is highly restrictive. It explains why black hole evaporation is such a delicate process theoretically. At the same time, classical geometry offers no place to store this information. A smooth horizon has no internal degrees of freedom. It cannot encode microscopic detail. The requirement of information conservation therefore implies that the classical description is incomplete. Spacetime must have additional structure that becomes relevant in extreme regimes. It is crucial to avoid overstatement. This conclusion does not imply violent breakdowns of spacetime or dramatic observable effects at horizons under ordinary conditions. The additional structure may be subtle and inaccessible to low-energy probes. Classical geometry may remain an excellent approximation for all practical purposes. The limitations appear only when information accounting is pushed to its limits. Different theoretical approaches propose different mechanisms. Some suggest that information is stored in degrees of freedom associated with the horizon. Others propose that information is encoded non-locally across spacetime. Still others suggest that spacetime itself emerges from entanglement. These approaches differ in detail, but they agree on the core constraint. Information must be preserved. The black hole information problem therefore reshapes the criteria for any theory of gravity. It is no longer sufficient to reproduce classical gravitational dynamics. A viable theory must also explain how spacetime encodes and releases information without violating unitarity. Geometry must be compatible with quantum information. This compatibility requirement reaches beyond black holes. If horizons of any kind hide information, then the same logic applies. Accelerating observers and cosmological horizons must also be described in a way that preserves information. The problem is universal. It is a property of spacetime rather than of particular solutions. At this stage, the classical separation between matter and geometry collapses. Information is carried by matter and by spacetime. Entropy counts states associated with both. Gravity must be treated as an information processing system as well as a geometric one. This shift does not resolve the information problem. It clarifies its meaning. The problem is not how to retrieve information in practice. It is how to describe spacetime in a way that makes information preservation possible. Any acceptable theory must encode this at a fundamental level. The conclusion is narrow but decisive. Information conservation is non-negotiable within quantum mechanics. Black holes force gravity to respect this requirement. Classical spacetime cannot do so on its own. A deeper description is required. This realization prepares the ground for a unifying principle. If information capacity is bounded and conserved, then the structure of spacetime must reflect those bounds. Geometry may be a manifestation of information constraints rather than a fundamental ingredient. The final implication follows from universality. The information problem is not confined to black holes formed from collapsing stars. It arises whenever spacetime contains a horizon that limits access to information. Any causal boundary that separates regions of spacetime enforces ignorance on an observer. If information is conserved, then that ignorance must be accounted for physically. Spacetime itself must encode the information that cannot be accessed directly. This realization elevates information from a bookkeeping concept to a physical constraint. Information conservation applies everywhere and always. It cannot be suspended by geometry. If spacetime hides information, then spacetime must also store it in some form. Horizons cannot be treated as mere mathematical surfaces. They must correspond to real degrees of freedom capable of carrying information. Once this step is taken, the role of entropy becomes sharper. Entropy associated with horizons cannot be dismissed as subjective ignorance. It must count genuine microstates. These microstates must evolve consistently with quantum mechanics. They must allow information to be preserved even when classical geometry suggests it is lost. Entropy therefore reflects structure rather than uncertainty. This requirement places strong limits on how spacetime can behave. It cannot be perfectly local in the classical sense. Locality would prevent information stored behind a horizon from influencing the outside. Some form of non-local encoding must exist. This non-locality does not imply faster than light signaling. It implies that the fundamental description of spacetime is not organized purely by local geometric relations. The conclusion must be handled carefully. Non-local information encoding does not mean that spacetime is ill-defined or that causality breaks down. It means that geometry is an effective description that emerges when information is coarse-grained. At the fundamental level, information may be distributed in ways that do not map cleanly onto classical spacetime points. This perspective aligns naturally with the entropy bounds discussed earlier. If information capacity is limited by area rather than volume, then the fundamental degrees of freedom cannot be independent at each point in space. They must be correlated in a way that reduces redundancy. Geometry then emerges as a way of organizing these correlations. The information problem therefore forces a rethinking of what spacetime is. Geometry cannot be fundamental if it cannot account for information conservation. It must arise from a deeper structure that already obeys quantum rules. Spacetime becomes a macroscopic manifestation of information relationships rather than a primary arena. At the same time, restraint remains essential. These conclusions do not specify the detailed nature of the underlying structure. They do not identify a unique microscopic theory. They establish constraints rather than solutions. Information must be conserved. Entropy must be accounted for. Geometry must be compatible with both. What has been achieved is a narrowing of ignorance. Entire classes of theories are ruled out. Any theory that allows fundamental information loss is unacceptable. Any theory that treats spacetime as a featureless continuum with unlimited information capacity is unacceptable. Gravity must encode information in a finite and conserved way. This narrowing sets the stage for the next conceptual step. If information capacity is bounded by area, and if spacetime geometry reflects that bound, then there must exist a principle that relates bulk physics to boundary information. Such a principle would explain why geometry behaves the way it does without treating it as fundamental. That principle will not claim that spacetime is an illusion. It will claim that spacetime is constrained by information. Geometry will appear as a derived description that reflects deeper informational limits. Exploring that idea requires introducing a framework in which information and geometry are linked explicitly. The constraints imposed by gravity, entropy, and information converge toward a single unavoidable idea. If the maximum entropy that can be contained within a region of spacetime scales with the area of its boundary rather than with its volume, then the fundamental description of that region cannot be fully contained within the space it occupies. A volume-based description overcounts physical states. Information must be encoded in a more economical way. This insight is known as the Holographic Principle. The principle does not originate as a speculative claim about reality. It originates as a bound. Black hole thermodynamics establishes that no system can possess more entropy than a black hole of the same size. Since black hole entropy scales with horizon area, this bound applies universally. Gravity enforces it dynamically. When a system threatens to exceed the bound spacetime, responds by forming a horizon. Geometry intervenes to protect information limits. The consequence is immediate. Ordinary quantum field theory assumes that each point in space carries independent degrees of freedom. This assumption leads naturally to entropy scaling with volume. Gravity forbids this. The holographic principle asserts that the true number of independent degrees of freedom describing a region grows only with the area of its boundary. The bulk description is redundant. The information required to describe everything inside can be encoded on a surface of one lower dimension. This statement must be interpreted carefully. It does not claim that physical processes literally take place on surfaces in any naive sense. It claims that information capacity is bounded by area and that any complete description must respect that bound. The bulk description remains useful and accurate at large scales. but it cannot be fundamental. The name holographic is precise rather than metaphorical. A hologram stores a three-dimensional image on a two-dimensional surface without loss of information. In gravitational systems, an analogous situation arises. The physics inside a region can be fully represented by degrees of freedom defined on its boundary. The extra dimension becomes emergent rather than fundamental. This idea gains sharp mathematical expression in specific theoretical constructions. In certain highly symmetric spacetimes, a precise equivalence can be established between a gravitational theory in a higher dimensional bulk and a quantum theory without gravity living on its boundary. The most well-studied example is known as ADS-CFT. In this correspondence, every physical quantity in the gravitational theory has an exact counterpart in the boundary theory. Energies, correlation functions, and dynamical processes match perfectly. The significance of this result cannot be overstated. It demonstrates that gravity and space-time geometry can emerge from a non-gravitational quantum system without contradiction. The bulk spacetime is not assumed. It is reconstructed from information encoded in the boundary theory. Geometry becomes a derived object. At the same time, strict limitations must be stated. These correspondences are exact only in specific spacetimes with particular boundary conditions. They are not proven to apply to our universe. They do not imply that spacetime everywhere behaves holographically in a simple way. What they demonstrate is logical possibility. Gravity can emerge from information under well-defined conditions. What makes the holographic principle compelling is not the existence of exact dualities alone. It is the way it unifies previously separate facts. Area scaling of entropy information, conservation horizon, thermodynamics, and non-local encoding all fit naturally into a holographic framework. What appeared as isolated coincidences become aspects of a single structure. This unification reshapes the meaning of geometry. Curvature ceases to be a fundamental field. It becomes a measure of how information is organized and entangled. Regions of strong curvature correspond to dense patterns of information. Flat regions correspond to simpler informational structure. Geometry summarizes relationships rather than defining them. Locality is also reinterpreted. In the bulk description, interactions appear local. Signals propagate through neighboring points. In the underlying description, locality may not exist in the same way. Information can be stored and processed non-locally, while still producing an effective local geometry at large scales. Causality is preserved even if locality is emergent. It is essential to emphasize restraint. Holography does not prove that spacetime is an illusion. It does not deny the reality of distance or duration. It denies that these quantities are fundamental. They emerge as effective descriptions once information is coarse-grained. The geometric picture works because it is the most efficient way to describe collective behavior. The holographic principle therefore shifts the central question. Instead of asking what spacetime is made of, the focus moves to how information is encoded and constrained. Geometry becomes a bookkeeping device that tracks information capacity and flow. Gravity becomes inseparable from information theory. This perspective does not discard general relativity. It explains its success. Geometry remains the correct macroscopic language for gravity. The equations of curvature remain accurate and predictive. Their origin is reinterpreted rather than denied. The significance of holography lies in what it forbids. It forbids treating spacetime as a featureless continuum with unlimited information capacity. It forbids local field theories as fundamental descriptions of gravity. It forbids ignoring entropy bounds. Any deeper theory must respect these constraints. At the same time, holography does not complete the story. It provides a framework, not a final theory. It shows that gravity can emerge from information. It does not show that it must. The distinction remains open. What is clear is that geometry behaves as if it reflects deeper informational limits. Curvature responds to energy in a way that preserves entropy bounds. Spacetime acts like a thermodynamic system whose macroscopic variables encode information relationships. This realization prepares the next step. If geometry reflects information constraints, then gravitational dynamics themselves may be derivable from thermodynamic principles. Gravity may behave like an equation of state rather than a fundamental force. Exploring that possibility requires examining how gravitational equations arise when entropy and information are treated as primary. The holographic viewpoint also forces a reassessment of what locality means in a gravitational universe. In ordinary physical theories, interactions occur between neighboring points in space. Causes propagate step by step through a fixed geometric background. This notion of locality is built into classical field theories and into quantum field theory. Holography suggests that this structure may be emergent rather than fundamental. In a holographic description, the fundamental degrees of freedom do not live throughout the bulk in an independent way. They reside in a lower dimensional description that encodes all physical information. Bulk locality arises only after information is reorganized into an effective geometric picture. At a fundamental level, correlations may be highly non-local, even though the emergent spacetime appears local at macroscopic scales. This non-locality does not imply violations of causality. Signals do not propagate faster than light in the emergent description. Instead, it implies that the underlying variables are not arranged according to the same spatial relationships that appear in geometry. Locality becomes a derived property that holds when information is coarse-grained in a particular way. What makes this plausible is the internal consistency of known holographic examples. In settings where the correspondence is precise bulk, gravitational dynamics are completely determined by quantum dynamics on the boundary. There is no additional freedom. Every bulk process corresponds to a boundary process that respects quantum causality and unitarity. Geometry emerges as a reorganization of information, not as an independent entity. This perspective reshapes how curvature is interpreted. Curvature no longer needs to be thought of as a fundamental field living on spacetime. It can be understood as a measure of how information is distributed and entangled. Regions of high curvature correspond to complex patterns of entanglement. Regions of low curvature correspond to simpler patterns. Geometry becomes an informational map. This interpretation does not depend on a specific microscopic model. It follows from the existence of entropy bounds and from the success of holographic constructions. Even without knowing the exact degrees of freedom, one can infer that geometry must reflect information, structure in some way. The relationship is constrained even if the mechanism is unknown. At the same time, it is essential to maintain the limits of the argument. Known holographic correspondences rely on idealized spacetimes with specific symmetries. They do not describe the expanding universe directly. There is no experimental confirmation that our universe admits an exact holographic dual. The principle is supported by theory, not by observation. Despite this limitation, the explanatory power is significant. Holography provides a natural explanation for why entropy scales with area. It explains how information can be preserved in the presence of horizons. It explains why geometry behaves thermodynamically. These features appear strained or mysterious in a purely geometric interpretation. They fit naturally in an information-based one. What changes most dramatically is the status of spacetime itself. Spacetime is no longer assumed as a primitive arena in which physics takes place. It becomes a derived construct that organizes information efficiently at large scales. Distance and duration become emergent quantities that summarize correlations rather than fundamental measures. This does not weaken the predictive power of general relativity. On the contrary, it explains its rigidity. The equations of curvature work because they capture universal information constraints in a geometric language. They are insensitive to microscopic detail for the same reason that thermodynamic laws are insensitive to molecular composition. The holographic principle, therefore, does not replace gravity. It reframes it. Gravity remains the correct macroscopic description of how energy and momentum influence geometry. What changes is the interpretation of that geometry. It becomes a manifestation of deeper informational limits rather than an independent substance. This reframing also clarifies what holography does not claim. It does not claim that space-time is unreal. It does not claim that physical processes are illusions. It claims that the deepest description of reality may not be geometric. Geometry may be the language that emerges when information is organized in a particular way. The principle, therefore, shifts the center of gravity in fundamental physics. Information and entropy move to the foreground. Geometry moves to the background as an effective description. Gravity appears increasingly as a consequence rather than a cause. With this shift in place, a natural question follows. If geometry reflects information constraints, then gravitational dynamics themselves may follow from thermodynamic reasoning. Instead of treating curvature equations as fundamental, one can ask whether they arise from entropy balance. This question leads directly to the idea that gravity behaves like a thermodynamic system. The final implication of holography concerns the status of gravitational laws themselves. If space-time geometry is an emergent description that reflects how information is organized, then the equations governing gravity may not be fundamental in the usual sense. They may be effective relations that summarize how information and entropy respond to energy and motion. Geometry would then play a role similar to pressure or temperature, rather than that of a microscopic variable. This possibility is not introduced by analogy alone. In holographic settings, gravitational dynamics in the bulk can be derived entirely from properties of the boundary theory. Changes in entanglement structure correspond directly to changes in bulk geometry. Curvature responds precisely as required to maintain consistency between energy entropy and information flow. Gravity behaves as a bookkeeping rule that enforces informational balance. It is essential to remain precise about what this does and does not imply. These derivations do not prove that gravity is emergent in our universe. They demonstrate that gravity can emerge from information in consistent theoretical models. They establish logical possibility, not empirical necessity. The distinction matters. Holography constrains gravity without dictating its ultimate nature. What cannot be ignored is the pattern that emerges. Entropy scales with area. Information is conserved. Horizons carry thermodynamic properties. Geometry responds to information constraints. These facts align naturally if gravity behaves thermodynamically. They appear far more mysterious if gravity is treated as a fundamental interaction independent of information. This perspective also clarifies why gravity has resisted straightforward quantization. If curvature is a macroscopic variable, then quantizing it directly may be analogous to quantizing pressure. The procedure may capture fluctuations without revealing the underlying degrees of freedom. The difficulty is conceptual rather than technical. The wrong variables may be treated as fundamental. At the same time, restraint remains essential. None of these arguments eliminate the geometric description. Geometry remains the correct language for gravity at accessible scales. The equations of general relativity remain exact within their domain. Holography explains their universality rather than undermining it. The holographic principle therefore marks a conceptual boundary. It shows that geometry need not be fundamental to be real. It can be emergent and still govern motion precisely. It reframes gravity as a manifestation of deeper informational constraints rather than an independent force. This reframing does not complete the story. It sharpens the next question. If geometry reflects information limits, then can gravitational equations themselves be derived from thermodynamic principles alone? If so, gravity may behave like an equation of state rather than a fundamental law. Exploring that possibility requires examining explicit derivations that treat entropy as primary and curvature as secondary. The holographic principle thus serves as a bridge. It connects entropy, bounds information conservation, and geometric dynamics into a single framework. It does not claim final answers, it constrains the direction of inquiry. With this framework in place, the focus shifts. Instead of asking what gravity is made of, the question becomes why gravity behaves the way it does. The answer may lie not in new forces or particles, but in the statistical behavior of information at the deepest level. The idea that gravity might behave like a thermodynamic system is not a metaphor introduced for intuition. It arises from explicit calculations that connect space-time dynamics to entropy and information balance. In carefully defined settings, the equations that govern space-time curvature can be derived from thermodynamic reasoning alone. Gravity appears not as a fundamental interaction imposed on space-time, but as a response required to maintain consistency between energy entropy and information. The key insight is local rather than global. Consider a small region of space-time near a horizon perceived by an accelerating observer. That observer detects a temperature associated with the horizon and attributes entropy to it. When energy flows across the horizon, the entropy changes, requiring that this energy flow obey the fundamental relation between energy, temperature, and entropy forces a specific response from space-time geometry. That response is precisely what is described by the gravitational field equations. In this derivation, curvature does not act as a dynamical field in the usual sense. It plays the role of a macroscopic variable, analogous to pressure in a fluid. The equations of gravity enforce a balance condition. They ensure that entropy accounting remains consistent for all observers, regardless of their state of motion. Geometry adjusts so that thermodynamic relations are preserved locally everywhere. What makes this result remarkable is how little input is required. No assumptions are made about the microscopic constituents of space-time. No specific model of quantum gravity is invoked. The derivation relies only on three elements. Horizons carry entropy. Energy is conserved. Thermodynamic relations hold universally. From these minimal assumptions, the structure of gravitational dynamics follows. This does not mean that gravity has been proven to be emergent. It means that gravity behaves exactly as if it were emergent from deeper statistical principles. The distinction is essential. The derivation shows compatibility, not identity. Gravity can be interpreted thermodynamically without contradiction. Whether it must be interpreted that way remains open. The thermodynamic perspective also explains why gravitational equations are universal. They do not depend on the type of matter involved or on microscopic details. They apply equally to all forms of energy. This universality mirrors the universality of thermodynamic laws. Pressure, volume, and temperature obey the same relations regardless of molecular composition. Gravity exhibits the same insensitivity. Another striking feature is locality. The derivation applies in arbitrarily small regions of space-time. Gravity emerges not from global assumptions about the universe, but from constraints that must hold locally for entropy and energy flow. This mirrors the structure of thermodynamics, which applies locally even in systems far from equilibrium. At the same time, the limits of the argument must be stated clearly. The derivations apply most cleanly near equilibrium. They assume the existence of local horizons and well-defined entropy. Extending the reasoning to fully dynamical regimes remains an open challenge. The results are powerful, but not all-encompassing. What they establish is a shift in perspective. Gravity no longer appears as a force that causes motion. It appears as a condition that space-time must satisfy to preserve information balance. Curvature becomes the response rather than the cause. Energy flow drives changes in geometry in the same way that energy flow drives changes in pressure and temperature. This perspective also sheds light on why gravitational dynamics are so rigid. The equations of gravity are not arbitrary. They are tightly constrained by thermodynamic consistency. There is little freedom to modify them without breaking entropy balance. This rigidity explains why attempts to alter gravity often encounter deep problems. It also reframes the meaning of explanation. The geometric description tells us how space-time curves. The thermodynamic description tells us why it must curve that way. The two descriptions are complementary. They describe the same physics at different levels. At this stage, gravity appears less like a fundamental interaction and more like an equation of state. It summarizes how space-time responds collectively to energy and information. This does not trivialize gravity. Equations of state are powerful and predictive. They encode deep information about underlying structure without revealing microscopic detail. The significance of this shift is not that it provides final answers. It narrows the landscape. Any theory of gravity must explain why gravitational dynamics can be derived from entropy considerations. Ignoring this fact is no longer viable. With gravity now behaving thermodynamically, the next question becomes unavoidable. If gravitational equations arise from entropy balance, then what are the microscopic degrees of freedom whose statistics produce space-time geometry? Answering that question will determine whether gravity is fundamental or emergent. The thermodynamic derivations also clarify what these results do and do not imply about the nature of gravity. Showing that gravitational equations can be obtained from entropy balance does not demonstrate that gravity is emergent in the same way that temperature emerges from molecular motion. It demonstrates that gravity is compatible with an emergent interpretation. Compatibility constrains theory space, but it does not decide ontology. This distinction is critical. A behavior that follows thermodynamic relations need not originate from thermodynamics. Pressure obeys an equation of state, but that equation does not explain atoms by itself. Likewise, gravitational equations may reflect deeper structure without revealing it. Gravity could be fundamental, yet so tightly constrained by information principles that it mimics thermodynamic behavior. Or gravity could arise entirely from microscopic degrees of freedom, whose collective dynamics appear geometric. Present results do not distinguish between these possibilities. What the thermodynamic perspective does establish is that geometry is not free to behave arbitrarily. Curvature must respond to energy in a way that preserves entropy balance for all observers. This requirement alone is powerful enough to fix the form of gravitational dynamics. The equations are not chosen, they are enforced by consistency. Geometry behaves as if it is an equation of state. This enforcement also sheds light on a long-standing puzzle. Attempts to quantize gravity directly by treating curvature as a fundamental field have encountered persistent conceptual obstacles. If curvature is a macroscopic variable, then this difficulty is not surprising. Quantizing pressure does not reveal the atomic structure of matter. Quantizing curvature may capture fluctuations without exposing the underlying degrees of freedom that give rise to space-time. At the same time, restraint remains essential. None of this diminishes the empirical success of general relativity. Geometry remains the correct language for gravity at accessible scales. The thermodynamic interpretation does not replace the geometric one. It explains its rigidity and universality. The equations work because they summarize collective behavior that is largely insensitive to microscopic detail. Another important clarification concerns proof. Thermodynamic derivations do not prove that gravity is emergent. They prove that gravity behaves as if it were emergent. Behavior and origin must not be conflated. The results show that gravitational dynamics can be understood without assuming geometry as fundamental. They do not show that geometry must be non-fundamental in reality. Nevertheless, the pattern is difficult to ignore. Space-time carries entropy. Horizons have temperature. Information is conserved. Entropy. Bounds restrict physical states. Gravitational equations enforce these constraints with extraordinary precision. These facts align naturally if gravity reflects deeper statistical behavior. They appear strained if gravity is treated as a standalone interaction unrelated to information. What changes most profoundly is the status of explanation. Geometry explains how gravity operates. Thermodynamics explains why it operates that way. The two perspectives are not competitors. They are complementary. Geometry provides description. Thermodynamics provides constraint. The cumulative picture now becomes clear. Gravity behaves geometrically. Geometry carries entropy. Entropy reflects missing information. Information obeys conservation laws. Gravitational dynamics emerge as the unique response that preserves information balance under energy flow. Each step is supported independently. Together, they point toward a deeper layer beneath classical spacetime. The open question is no longer whether gravity resembles thermodynamics. It does. The question is whether this resemblance is superficial or fundamental. Is gravity constrained by information or produced by it? Current physics does not yet decide. What it does decide is that any satisfactory theory must account for this relationship. This narrowing of possibilities marks a transition. Gravity can no longer be understood purely as curvature, nor purely as force. It sits at the intersection of geometry, thermodynamics, and information. Any deeper description must unify all three without discarding established results. What follows will not be settled physics. It will be careful exploration of an open question. Whether gravity is fundamental or emergent remains unresolved, but the criteria for answering that question are now sharply defined. At this point, the question can no longer be postponed. Gravity behaves geometrically, yet carries entropy. Space-time responds to energy while enforcing information bounds. Gravitational dynamics can be derived from thermodynamic reasoning under broad conditions. These facts force a reassessment of what gravity actually is. The issue is no longer philosophical. It is imposed by consistency with established physics. One possible interpretation is that gravity is fundamental but uniquely constrained. In this view, gravity is a basic interaction unlike any other. It is not mediated by exchange particles in the usual sense, and it cannot be isolated from spacetime itself. Its equations are rigid because they must respect entropy bounds and information conservation. Geometry is fundamental, but tightly restricted by deeper principles. Another possibility is that gravity is emergent. In this view, gravity is not a primary interaction at all. It arises from the collective behavior of microscopic degrees of freedom, whose statistics obey quantum mechanics. Curvature appears as a macroscopic variable, similar to pressure or temperature. Objects move under gravity, not because a force acts on them, but because space-time geometry adjusts in response to information gradients. One prominent proposal along these lines is often referred to as entropic gravity. In this framework, gravitational behavior arises when systems evolve toward configurations of higher entropy. Motion under gravity reflects statistical tendency rather than fundamental interaction. Energy gradients correspond to information gradients, and geometry responds accordingly. The motivation for such ideas is mathematical rather than aesthetic. Under specific assumptions, relationships between energy entropy and displacement can reproduce familiar gravitational behavior. Gravity appears as a consequence of information balance, rather than a force mediated by fields. This approach attempts to explain why gravity is universal, and why it couples to all forms of energy without exception. However, restraint is essential. These ideas remain hypotheses. They do not replace general relativity. They do not yet reproduce all of its tested predictions in all regimes. They rely on assumptions about information storage and entropy change that are not yet derived from a complete microscopic theory. No experimental evidence currently distinguishes emergent gravity from conventional explanations. A particularly sharp challenge arises from astrophysical observations attributed to dark matter. Standard cosmology explains galaxy rotation curves, gravitational lensing, and large-scale structure through the presence of unseen matter. Any modification or emergent description of gravity must reproduce this empirical success without contradiction. Current entropic models have not yet achieved this conclusively. This limits their scope, but does not eliminate their conceptual relevance. What matters is not whether a specific, emergent model is correct. What matters is that gravity can be questioned at a foundational level without contradicting known physics. The possibility that gravity is emergent is no longer speculative storytelling. It is a constrained research direction shaped by entropy, bounds holography, and information conservation. At the same time, the alternative remains viable. Gravity may be fundamental, but constrained by information in a way unlike any other interaction. In this view, spacetime geometry is primary, but must obey thermodynamic consistency. Entropy and information do not generate gravity, but restrict it. Geometry remains basic, but not arbitrary. Current physics does not decide between these possibilities. What it does decide is what gravity cannot be. Gravity cannot be fully explained by Newtonian force laws. It cannot be fully explained by classical curvature alone. It cannot be independent of information. These conclusions follow directly from black hole thermodynamics entropy, bounds, and quantum consistency. The deeper lesson is methodological. Physics advances by identifying which questions are unavoidable. The microscopic origin of spacetime is now unavoidable. The role of information in gravitational dynamics is now unavoidable. Any theory that ignores these questions is incomplete, regardless of mathematical elegance. The question posed at the beginning can now be stated precisely. Is spacetime curvature a fundamental feature of reality? Or is it an effective description of how information is organized? Both possibilities remain open, but neither is unconstrained. Any viable answer must explain why spacetime carries entropy, why horizons obey thermodynamic laws, and why gravity responds universally to energy. No final conclusion is claimed. The evidence does not allow one. What has been achieved is a narrowing of ignorance. Gravity has been traced from force to geometry, from geometry to entropy, and from entropy to information. Each step is grounded in established physics. Together, they reveal a structure deeper than classical spacetime. Gravity remains the most familiar interaction and the least understood. Its effects are measured with extraordinary precision. Its origin remains open. Whether gravity is fundamental or emergent, the final theory will not discard geometry. It will explain why geometry works. Gravity now stands as a boundary concept. It marks the interface between what is known and what must still be discovered.